When we first learn classical mechanics, we solve problems by treating objects as perfect dimensionless dots. We calculate trajectories assuming a car, a planet, or a baseball is just a single point mass moving freely through empty space. But real physical objects are extended bodies. They have finite size, and they are made of countless individual particles that are constantly rotating, vibrating, and shifting relative to one another. Look at this geometric block sliding down an incline. Because it doesn't rotate or tumble, every single particle inside this block moves with the exact same velocity at any given instant. This is pure translational motion. Now replace the sliding block with a rolling cylinder on the exact same plane. By tracing the paths of specific points on its outer edge, we see they don't move in straight lines. They trace out complex, overlapping curves called cycloids. The velocity vectors for these peripheral particles constantly change in both size and direction at every fraction of a second. Even the point making contact with the ramp has a momentary velocity of 0. Mapping the individual trajectory and velocity of every particle in an extended body requires solving a separate kinematic equation for each one, a calculation that grows exponentially as the body becomes more complex. But if we filter out the looping paths of the outer edges, we can isolate a single coordinate, the exact geometric center of the rolling cylinder. Track only this coordinate, and its trajectory draws a perfectly straight line, completely parallel to the ramp. It matches the pure translation of our sliding block. This specific location isolates the pure translational component of the cylinder's motion, effectively ignoring the rotation of the surrounding material. Physicists call this unique coordinate the center of mass. Defining and locating this one point allows us to track the overall movement of any real-world extended body without needing to calculate the specific paths of its internal parts. To understand exactly how this coordinate is calculated, we begin with a foundational one-dimensional system containing just two distinct particles. Here is a horizontal x-axis with a defined origin point, O. We have two particles with masses m1 and m2, plotted at specific distances x1 and x2 from that origin. The exact coordinate for the center of mass, capital X, is found by multiplying each mass by its position, adding those together, and dividing by the total mass. This equation defines the mass-weighted mean position for the system. If the two masses are equal, the mathematics force that center point to rest exactly midway between them. This logic scales directly into two dimensions by adding a third mass and tracking positions across an xy plane. Consider a system of three equal masses arranged at the vertices of an equilateral triangle. By computing the mass-weighted mean for the x and y coordinates independently, the resulting center of mass coordinate falls exactly onto the triangle's geometric centroid. We can expand this framework into three-dimensional space to account for any number of discrete particles. Using position vectors, denoted as Ri, we have a mathematical shorthand to track the location of every particle simultaneously in 3D space. This yields a generalized equation. Using the sigma summation symbol, we total the product of mass and position for every individual piece and divide by the total system mass, m, to find capital R, the position vector for the center of mass. It is important to note that capital R doesn't necessarily point to a piece of physical matter. The center of mass is a geometric coordinate derived from how mass is distributed in space. This discrete model works for scattered points, but we need a bridge to solid, continuous, rigid bodies, like a rod or a sphere. A solid object contains millions of microscopic particles packed together. In such cases, executing a discrete summation for every individual atom is mathematically impractical. Instead, we subdivide the continuous body into a high number of tiny, localized mass elements, labeled delta Mi. As the number of these elements approaches infinity and their individual size shrinks toward 0, the discrete summation symbol is transformed into a continuous integral. This provides the calculus definition of the center of mass, where the position vectors are integrated over all mass elements, dm, across the entire body. While these integrals can be complex, we can often determine the center of mass using a shortcut called reflection symmetry. Take a uniform thin rod. If we place the mathematical origin of our coordinate system exactly at the rod's geometric center, we find that for every small mass element dm at a positive distance x, there is a mirror mass element at negative x. When we integrate across the rod, every positive segment cancels its negative partner. The entire integral sums to 0, confirming the center of mass rests precisely at the geometric center. Because this coordinate depends on the distribution of mass, it can even sit in empty space where no material exists. Look at this uniform L-shaped flat plate. If we subdivide it into 3 equal squares, symmetry tells us the center of mass for each individual square sits at its own centroid. By calculating the mass-weighted mean of these 3 points, the final center of mass falls outside the material of the plate entirely. With the geometry of this single coordinate established, we can now examine how it behaves under the influence of physical forces. To move from geometric statics to dynamics, we must determine how the center of mass coordinate moves through time. We start with the base position vector equation. Total mass m times the center vector r equals the sum of each individual mass times its position vector, ri. Differentiating both sides with respect to time gives us the rate of change. The position vectors for the particles and the center of mass mathematically transform into velocity vectors. Differentiating a second time yields acceleration. The velocity of the center of mass, v, becomes acceleration a, and the particle velocities become individual accelerations. Through calculus, we have linked the geometric center of mass directly to the dynamic acceleration of the entire extended body. Recall Newton's second law for a single particle. Mass times acceleration equals the total applied force. We can apply this concept to our system equation. Each instance of mass times acceleration for a particle represents the total force acting on that particle. The total force acting on a system consists of 2 parts: external forces applied from outside the body and internal forces that particles exert on each other. Within the system, Newton's third law dictates that every internal force between 2 particles has an equal and opposite partner. When we sum these forces across the entire collection, every internal interaction pair mathematically sums to 0. Because they cancel out in the final summation, internal forces drop out of our equation entirely, leaving only the external forces. This leads to our final derived result. The sum of the external forces equals the total mass of the system times the acceleration of the center of mass. This means any complex body moves exactly as if its entire mass were concentrated at a single geometric point, accelerated only by external forces. This proof provides the mathematical basis for the point mass approximation. It demonstrates that we can track the overall trajectory of any system by focusing on a single coordinate, regardless of its internal motion.